Swayam Prabha. Digital India. Educated India.
Okay. So consider the greedy solution. We are using the same technique as before. Consider the greedy solution. So here G1 means the weight of item 1. Item 1 is the item with the largest PI. Okay, this is sorted by PI. Okay, so G1 is the weight of the weight taken by the greedy solution of item 1 and so on. Okay. Okay. Now similarly take any other solution S, okay, and your idea is to convert S into G without changing the quality of S or without changing the profit of S. Okay. So this is similar to it. Consider the first index where G and S are not the same. Okay, right. Now by the way greedy is chosen, GI greater than SI, right? Greedy will take, so profit of ith item is greater than profit, so greedy will take the maximum possible amount from of the ith item. That's how our algorithm works, right? So GI should be greater than SI. Okay. Now what you'll do is to transform, you will take whatever is right. So in S initially had SI of item I. Now you will add some more of item I to S, so that it becomes GI of item I. Okay. So you exchange these items and to get a new solution S prime. I am not going into the details, but you can show that while after doing this exchange, the total cost of S prime is not reducing. Uses the property that GI is greater than SI. Okay. You can work that out and continue the exchange and till S becomes exactly the same as GI is the weight taken of item I. Yes. By greedy algorithm, you take the maximum possible values of the item you choose, right? First item, how much ever possible, you take that much. Okay. So GI would have taken the entire available quantity of item I or whatever is the remaining, right? SI cannot take more than that. SI cannot be larger than that. Then our greedy would have taken that much. So his question was, what if fractional, it is not allowed to take fractional amounts. You have to take either the entire weight of an item or nothing at all. Then this will not work. Of course, I think that the same counter example will work. Running time for this, we already done that. Next, yeah, my most interesting technique, dynamic programming. Okay, so yeah, I don't know how to define dynamic programming in 1 or 2 lines. So we'll start with when dynamic programming is applicable. So dynamic programming is applicable when the problem has an optimal substructure. What do I mean by optimal substructure is you have an entire instance, you have a solution for that. Now you take a smaller part of the solution and solve only that smaller part, you get a solution, right? So this smaller solution can be used to get to the final large solution that you are looking for. Okay, so actually greedy divide and conquer, like the examples we have seen so far, have used optimal substructure in one way. So even dynamic programming need optimal substructure, and also the subproblems are overlapping. We'll explain that a little later. So let's start with the problem. Okay, we are trying to solve it. Max, yes. Some of them. It might not have other, like, overlapping subproblems. Okay, but again depends on the problem. So some problems are solvable by dynamic and divide and conquer. And even these techniques can be applied in many ways, right? So that's a pretty subjective. Okay. So maximum independent set in a graph, sorry, in a path. Okay. So you are given a graph which is a path. What does that mean? It's okay. So you are given a graph where, let's say, the vertices can be denoted as V1, V2, V3 to up to Vn, and the edges are such that between Vi and Vi plus 1 you have an edge. This is a path, a graph which is a path. Okay, and moreover this is weighted. That means every vertex has a, this is a vertex weighted graph. Every vertex has a weight associated with it. Okay, and you want to find maximum independent set. That means, what is an independent set? Subset of vertices which are pairwise non-adjacent. Okay, so in this case you can say that if you take some Vi, you cannot choose the next vertex Vi plus 1 because they have an edge. Okay, and you want to find a subset or find an independent set such that their total sum of their weights is maximized. So is the problem clear? Okay. So what happens if the graph is not weighted, or if the weights are all uniform? Okay, so we are given, let's say this is not there, the weights are not there. What is a maximum independent set in this graph? Alternating vertices. Either you take all the, yes, odd number or even number based on n. That will be the maximum independent set. So in an unweighted graph, it's a trivial question. Can you use the same technique here in a weighted, like take alternating vertices? Of course, it's a feasible solution, but is it an optimal solution? Is it always an optimal solution? No, right? Need not be. Can you think of a counterexample? Oh, okay. Then, okay. So, I think what you're suggesting is, let's say I'm taking the first, third, fifth vertices. Maybe 2, 4, 6 is the best. So, okay, then the second algorithm, what if I take 1, 3, 5 and so on, find their weight, total weight, take 2, 4, 6 and so on, and again take their weight. Whichever has the maximum weight, I choose that. Will that work? That might be possible, right? Like for example, if you have this V1, V2, V3, V4 and the weights are like this. Enumerate possible combinations of what? Vertices. You're essentially saying brute force. Oh, okay, if that is true, it's bad news for us, right? You're saying that brute force is the best. Okay, right. So here, what is the maximum independent set? 1 and 4, right? But if you take the odd and even, both they are suboptimal. Oh. So obviously that won't work. Okay. So let's see what we can do. So I said optimal substructure, right? Okay, we'll see whether the optimal substructure is there or not. So first, let's start with defining a subproblem. Okay. course, we are trying to use optimal substructure in some way. So, first let's have a sub problem, think of a sub problem. So, I define my sub problem like this. MIS of I is the value of maximum independent set of the subgraph V1 to V2 up to Vi. Okay, right. So, this is how I define my sub problem. It's clear that MIS of n is what we are looking for, right? The MIS of n, you are considering the entire graph, and the maximum independent set in that graph is what you are looking for. Okay, so let's try to solve MIS of I, or find the value of MIS of I. Okay, let's try find the value first. Okay, so the definition clear? What is MIS of I? Essentially, you are given a graph with I vertices, okay, and you want to find and weights, and you want to find the maximum independent set of this. Okay. Okay, so how will we solve it? So let's say, okay, so let's say at this point I get this hint. A little angel come and tell me that, okay, I'll give you a hint about the solution for MIS of I, the value of MIS of I. So what is the hint? The angel is going to tell me, okay, and the angel may not give me the entire answer. The angel will tell whether the ith vertex or the last vertex, whether it is part of the independent set or not. Okay, so I know this now. So how will it help us? So, okay, now I know, I have this knowledge whether the last vertex is part of the solution or not. Okay, so let's say that what angel has told me is, see, the last vertex is not part of the solution. Your maximum independent set till Vi does not contain Vi. So what can I say about the solution? Can I solve the solution now? So now I am in so this is my graph. Okay. The angel has told me that this vertex is not in the solution. Then what is the solution of this graph? What is the maximum independent set of this graph? It is the same as the solution of the graph till Vi minus 1, right? Anyway, Vi is not part of my solution for MIS of I. Okay. So in that case, MIS of I is same as MIS of I minus 1. Okay, right. So now I know how to solve the problem if the angel have told me that last vertex is not part of the solution. What if the angel told you that last vertex is part of the solution? Subtract what? Last. The last one is part of the solution, so it is included. So what can I say about this? Okay, okay, plus the weight. Okay, so ith vertex is part of the solution, so Wi, the weight of I is included. What is the rest of the solution? Is it I minus 1? Okay, why not I minus 1? Because I minus 1, like the optimum solution for I minus 1 might contain I minus 1, right? Angel has only told him about the solution for I don't know what solution of I minus 1. So it is not possible to have both I minus 1 and I in my solution. Okay, so so this cannot be the answer. So you know that if this is part of the solution, this is not the solution, and the rest of the solution will be the best till MIS or the I minus 2 vertex. Okay, right, good. So, okay, so if I know this, if I know Vi is not in the solution, then I say that the solution is MIS of I minus 1. If if Vi is in the solution, then the solution is Wi plus MIS of I minus 2. Okay, but it's highly unlikely that an angel is coming, it's going to tell me some hint, right? Okay. Hasn't happened to me before. Okay, so let's roll, let's leave that option out. Okay, so that's not going to help. But you know that exactly one of these cases should happen. Your solution can have only one of these. Either the ith vertex is in the solution or ith vertex is not in the solution. Right? That means one of these should be the correct answer. Right? Either MIS of I minus 1 or Wi plus MIS I minus 2 should be the correct answer. Right? So you just have to decide which one. Which one? How will you choose which one is the correct? What are you trying? What are you going to do? Pick which one of them? Bigger one of them, right? You are trying to maximize independent set, and each of them corresponds to a feasible solution. Whichever, and one of them is the correct answer. The maximum one should be the correct answer. Okay, right. So now you know this, that MIS of I is max of these two values. Okay. If you know this, right, you know how to run the algorithm. N equal to 0, use recursion, return 0, n equal to 1, return W1, otherwise use call the recursive functions. Yeah, the problem is just after that. If you are writing this algorithm, what is the running time of this algorithm? T of n is T of n minus 1, you have a recursively calling the MIS of n minus 1 and MIS of n minus 2. So T of n minus 1 plus T of n minus 2 plus 1, the running time is 2 power n. At this point, you are not looking for an exponential time running time, right? You are looking for polynomial. Okay, right. So, okay, so this algorithm is not enough for us, but can we take something away from this idea? So let's think about why this happened. Why this exponential running time? What's happening is this: you are calling MIS of n, which will recursively call n minus 1 and n minus 2. Now n minus 1 will again call n minus 2 and n minus 3, and on the right side n minus 2 will call n minus 3 and n minus 4. And here again n minus 2 will call n minus 3 and minus 4 and so on. Okay. So this is why the running time is 2 power n. This tree has height, has total size 2 power n. Actually it's slightly less than 2 power n. Okay. But if you notice this, you can see that, see, there are, you are computing the same thing in more than one branch. Okay, like n minus 2 and n minus 2 and n minus 3 you are computing here. So this is what I mean by overlapping subproblems. So you have subproblems, and each run for, or each solution for the solution for each subproblem has further subproblems which are overlapping. Okay. So this is what is causing our running time to be exponential. So what you can ask is this. Let's look at this. See, this last line, max, this takes only constant time if you already know the value of MIS of n minus 2 and MIS of n minus 1, right? Okay. So why not calculate that first instead of calling a recursive function? Okay. So what I am saying is, so we are doing it top down. We are starting with n, then trying to solve n minus 1, n minus 2 and go on. Instead of that, do it bottom up. Start with n equal to the small value 1. Find MIS of 1, then find MIS of 2, then use those values to find MIS of 3 and so on. In short, something like this. Okay. So MIS of 1, W1, 2, and after that find MIS of I for values of I from 3 to n, and finally return the value of n. Okay. What will be the running time of this algorithm? It's the order of n, right? It's just one loop which iterates n times, and the statement inside the loop takes only constant time. So this is the third principle that you use in dynamic programming, is you store or you compute the values for smaller solutions for smaller subproblems first and store it. And this is called memoization. So these are some of the elements of dynamic programming. So you are solving problems with optimal substructure and overlapping subproblems, and finally you are using memoization for improving the running time. Okay. And in general, dynamic programming is useful when these conditions are true, when there are only a small number of subproblems. Here by small I means polynomial, and the solution to the original problem can be computed from or using the solutions of smaller subproblems, and also there is a natural ordering on subproblems for smallest to largest. This is needed so that you can solve the subproblems from the smallest, and finally to the largest. Okay, right. And in a dynamic programming, these are the steps that you usually that's what we just like. Top down means you are recursively solving the smaller ones. So that will increase when there are overlapping subproblems. You are like, it becomes exponential. For the specific problem or in general, you say there can be cases like that. I'm not saying that dynamic programming can solve any problem. There are some problems for which dynamic programming is applicable. Okay. There can be problems where bottom up will help. But if you are using recursion, the running time will explode. That's what we just said. Recursion, but memoization basically means that you're storing the values of smaller values, at least in this case. In recursion, you don't know the smaller values, right? You're starting from the first. That's what we did. Then it becomes bottom up. There can be problems which can be efficiently solved using recursion also. That's what you're question. Like, I don't know. Of course, basically, like all this, cannot think of one thing now. Like whatever the dynamic program, the divide and conquer, they can be implemented using recursion, but that was fine. For example, the merge sort, it uses recursion, but they are like independent subproblems. Here they are like overlapping, they are not very independent. That's why the top down is not efficient. So, by designing a DP algorithm, these are like the general steps. You start by identifying a subproblem. Okay, and second step is define a recurrence for the subproblem. So in this case, you usually like what we say is like make a choice or make a guess. For example, in this independent set, for defining the recurrence, we started by making this choice between whether the last vertex is in the solution or last vertex is not in the solution. Usually referred to as like we guess whether the last vertex is in the solution or not in the solution. When I say I guess, I mean that I iterate over all possible choices or possible values for that and take the best out of it. So that is that's how you define a recurrence, and finally you implement in a bottom up way. And yes, proof of correctness usually come easier in dynamic programming algorithm. Yes. Yes. The question you asked, 01 knapsack. Someone. Okay, so we are given a knapsack. The same question, we are given a knapsack with capacity K. We are given n items with maximum weight available. Let's choose like optimum cost for, or let's say that cost is same as the weight. Pack the knapsack with as many items as possible. Total weight is maximized. One more constraint here. You can either pick the entire WI of item I or not pick anything at all. Okay. So will the greedy strategy work? Greedy will choose anyway it is uniform profit, so that's not work. So yes, what will be the solution for this? Here, yeah, it is C to C. Huh? Weights are there. Cost is same as weight. It's uniform 2 and 2. 2 and 2 is the best, right? Okay, so in general, how do you solve it? Any of the greedy strategies work? Like, so for example, here the greedy will tell you to take 3, right? That will give you the maximum. It's not per weight, per unit weight, but still 3 has the maximum profit. If you take 3, it will not. You cannot pack anything else. Okay, right? So it won't work. Okay. Okay. So we'll use dynamic programming for this. Step 1, define a subproblem. You want to look at subproblems and we will write a recurrence for it. So what is a subproblem you want to? If you're removing, how will it be maximum? Before removing, yes, more, right? Now, I want to write like define a subproblem, something like this. Okay. Opt of. So you are given n items and k is. So let's order the items from 1 to n. Okay. And find the optimum using I of them. Okay. And let's say this is the max capacity for I. So opt of I comma w, this is a subproblem I define. So value of the optimal solution using a subset of items 1 to k from 1 to I, and the maximum allowed capacity here is w. Okay. So if you solve this, you have solved the problem because opt n comma k is the result that you are looking for. Okay. So this is the subproblem. Next, you want to write the recurrence for it. Okay. So I said we'll make a choice or we'll make a guess about the solution. Okay. So this is okay. Even before going there, do you want to guess anything else? Okay. So let's try this. If item I part of the solution, okay, recall what I am trying to solve is what is the maximum weight of objects or items from 1 to I that I can pack such that my maximum capacity is within W, capital W. Okay. So what is the answer? Like, is item I part of the solution? If what happens if the ith or the last item is not part of the solution? These are two cases with respect to item I, right? Whether ith item is in the solution or it is not in the solution. What happens if it is not in the solution? Then what is the solution? I minus 1 and W. Okay. What happens if it is part of the solution? I minus 1 again, you can, yes. Yeah, it is of course weight of Wi plus I minus 1 and the capacity has changed, right? W minus W. Okay. So if item I is not part of the solution, then opt of IW is this. Otherwise, opt of IW is Wi plus opt I minus 1 W minus Wi, and one of them should be the correct answer. What is the correct answer? We are trying to maximize, so max of this. Yes, running time. Yeah, so one easy way to find the running time for DP algorithms is this. So you have this recurrence, right? You okay? So you can think of storing these values in a table, a DP table, right? So you want to calculate each entry in the table. So first, how many entries are there? So in here, how many entries are there? You have an entry for each I, where I goes from 1 to n, and each W, where W goes from 1 to k. So how many entries are there? N times k, right? And what next? What is the time taken to compute one entry? Assuming the smaller values are known, here this is a max of two values, right? Constant. So the running time for this is number of entries times time taken to compute one entry, which is nk times constant nk. So we have seen a maximum independent set in a path. What can you say about a maximum independent set in a tree? Let's say that it's a rooted tree. There's a root, let's call it R. You want to find a subset of vertices which are pairwise disjoint. Idea is to use dynamic programming. Okay, so step 1. Before, do you want to try any other solution, like any other techniques? Greedy, you can try it. Okay, so if you're using dynamic programming, step 1, subproblem. Define a subproblem. It's not always the best. You can think of counterexamples. Alternate levels may not, and also it's an arbitrary tree. Like I'm not considering a full tree or a complete tree. So we had a order in path, right? We had a linear order that made subproblems easy, like defining subproblems easy. But trees also have an order, right? A subset of vertices which are pairwise non-adjacent. They don't, like, you have a subset and you want to maximize the cardinality of such a set. So independent set is a subset, let's call it I, such that two vertices are in I, then they don't have an edge between them. So this is the subproblem. Maximum independent set in the subtree rooted at node U. Okay, so when you have a tree, what do you mean by this? So if you take a node, the subtree rooted at this node is this. All its the node, its children and its grandchildren and so on. And for this node, for example, it is this. For a leaf, it is just this. Okay. So you define the subproblem for the subtree. So if this is V, MIS of V means the maximum independent set for this subtree. Okay. Now, what is the subtree rooted at the root? The entire tree, right? And so if we compute MIS of R, then we get our solution we are looking. So the ordering here is from levels. So starting from leaves, so you compute MIS of vertices or nodes in the which are leaves, and then look at their parents and so on. Finally, you will reach the root. Okay. Okay. So subproblem is ready. Recurrence. First, we want to decide what we want to guess about the problem solution. What property of the solution we want to. If we go by our previous things, it's almost the same. So you can guess whether the root is part of the solution or not. Let's say that you are in a, okay, this is the tree or subtree that you are solving. Okay. So you will guess whether this node, the root, is in the solution or not in the solution. Okay. So what happens if R is not in the solution? Then what is the rest of the solution? Why, Max? You can add them, right? So if this R is not in the solution, then the maximum independent set of the graph is the maximum independent set for this plus the maximum independent set for. So basically it is, you can add up all the child nodes, whatever is the solution for all the child nodes. Okay. So what if R is in the solution? See, when we are writing the recurrence, we don't know about the child nodes. So how do you decide? How do you know whether it is? Yes. Okay. I think what you're saying is, if you have the root, you cannot have the child node, right? Okay. So so you cannot take the maximum here because it may contain this node, the child node. So what you're suggesting is, if the child node is there, don't take that. We cannot have it, right? So what is the, how can you say it with respect to smaller subproblems or in terms of smaller subproblems? Yes. Okay. Look at the grandchild nodes, grandchildren, and find their maximum independent set and add all. Okay. And yeah, so you compute both these and return the maximum. So maximum independent set U for given U is summation of MIS of V, where V is the child node, or some WI, the weight WU should have been WU, the weight of the root U in case it's weighted, otherwise it's just 1, plus summation of MIS of V, where V is the grandchild. Let's say this is your tree. Okay. So if the solution does not contain this, then the solution for this entire tree is the sum of the solution for this, this, and this. That is clear to you, right? If the solution contains the root node, you cannot take the maximum independent set of this, because that might contain this node. Then you cannot have both of them together at the same time. But so anyway, whatever you get from this part of the graph cannot contain this vertex. Okay. So that is equivalent to saying that you take the grandchild. No, if this is part of it, this cannot be part of the independence, right? So you are in the case where this is part of independence. Okay? So that's why you are taking this. You're finding the solutions, optimal solutions for the grandchild subtrees and adding. Anyway, this is not going to be part, right? So you can leave that. Okay, so I'll stop here. You can think of the running time for this algorithm. Yes. See, you are only calling solutions from that level. That does not imply that those nodes are in part of that solution. You cannot, first of all, it is not true to say that you take one node from ith level, you take all nodes from ith level. May not be true. Think for the counterexample. If you don't get it, it's an easy counterexample. Okay.